In today's tutorial, we will discuss the mechanistic details of the formation of these two sulfur heterocycles, a 5-membered and a 6-membered ring, starting from this acyclic compound with a thioether functionality and an olefin. Please stop the video first to make your own considerations and listen afterwards to the explanations I have to offer. So, bromine, elemental bromine, is the reactant in the first step, and this looks like an addition of bromine to an olefin. And as we know, a bromonium cation is usually the reactive intermediate in such a reaction. Let's draw this intermediate. The bromonium cation is a 3-membered ring with a cationic bromine, and of course the corresponding anion is also present. Now, the sulfur can react as a nucleophile, for instance reacting here in some kind of SN2 reaction. Then the 5-membered ring is already formed. And we now have a 3-bonded sulfur, which is the center of the cationic charge, and the bromide anion is of course also present. What kind of cyclization is it? A 5-membered ring is formed, and according to Baldwin's classification, we write down a 5 first, then it is reaction takes place at an sp3 hybridized carbon. Therefore, we have to add tet as the ending for tetragonal, and the bond which is broken is located outside of that ring, and therefore we add an exo in between. It's a 5-exo tet cyclization according to Baldwin. Now we have to get rid of that benzyl group. How can this happen? Simply by a substitution, also nucleophilic substitution, either as an SN2 or an SN1 process, since a benzyl cation would be involved in the substitution process, and the benzyl cation is, as we know, very good stabilized mesomerically. Also an SN1 process could occur. This heterocycle is the leaving group, and the substitution takes place, resulting in the formation of benzyl bromide. Of course, you can suggest that the bromide could also make that nucleophilic substitution on this stage of the reaction. This is indeed the case, it can happen. Then we have the classical addition of bromine to the olefin. Nevertheless, also from this competing product, a reaction path to the heterocyclic formation is present, simply that the sulfur is substituting intramolecular than this bromide. So, also this route here, this step, is the 5-exotet cyclization. So, we are now here at this stage at the 5-membered ring, and thermal transformation is reported. How does this work? Well, best explanation is that again an intramolecular substitution takes place. Sulfur as the nucleophile, bromide as the group. Sulfur, the center of 3 bonded, therefore the center of the positive charge. We have the bromide and iron. And if it reacts as a nucleophile here, then we would react backwards to get to a 5-membered heterocycle. So it's an equilibrium reaction, but if it reacts here, then we end up at the 6-membered ring. And since this is also equilibrium reaction, however, as the 6-membered ring is thermodynamically more favored, wait a while and this will be the main product present. One could think about an alternative mechanism. Let's assume that an SN1 process with question mark takes place. Then we would have a secondary cation here. And one could imagine that some kind of Wagner-Meerwein process, rearrangement, can take place. This carbon migrating and takes the electron pair with it. Then also a 6-membered ring is formed with the methyl group here, and there is the cation, which might be mesomerically stabilized by the sulfur. Now the bromide could add to the cation, the neutral molecule will result with this structure, bromine here, methyl group there. And as you see, it's an isomer, it's a structural isomer. The bromide and the methyl group have exchanged the positions. Well, okay, we had a rearrangement reaction taking place here. However, it is reported that this is the main product at the end of this reaction sequence. So we have to ask, what would disfavor this type of process? Maybe it's simply because this secondary cation is not as mesomerically stabilized as we thought, because the sulfur isn't able to stabilize mesomerically in the same way as an oxygen would do so, because the overlap of the orbitals is less favored here, because the sulfur simply is much bigger than the oxygen. Thanks for listening. See you next time again.